Now let's look at our first topic in this lesson, topic A, choosing the number of clusters. In the previous lesson, we just used a predefined number of clusters, but in real life, we don't always know what number of clustering to expect. There are different ways of trying to come up with the correct number of clusters. There are different ways of trying to come up with the correct number of clusters. We will learn about simple visual inspection, which has the advantages of being easy and intuitive, but relies heavily on individual judgment and subjectivity. We will then learn about the elbow method with sum of squared errors, which is partially quantitative but still relies on individual judgment and is more abstract than choosing based on visual inspection. Later in this lesson, we will also learn about using the silhouette score, which removes subjectivity from the judgment but is also quite abstract. We can visualize data and make a judgment about how well clusters are captured. Clustered points should be close to each other and further from other clusters. Now, there are some advantages as well as disadvantages. It is usually best with simple data with few dimensions. On the disadvantageous side, it relies heavily on individual evaluation. It is very subjective. And on the advantageous side, again, we can say that it's easy and intuitive. Now, why don't we go ahead and do an exercise to see what we're talking about here? Choosing the number of clusters based on visual inspection. In this exercise, we will apply k-means clustering to age and income data using different numbers of clusters ranging from 2 to 6, and we will use visual inspection to evaluate the results. First, I imported pandas and load the age and income data from the ageinc.csv dataset into a data frame named ageinc_df. Now I imported the matplotlib library and plotted a scatter plot of the age and income. Now look carefully at the plot we did, which should look like the one you see on the screen. You may already notice that the data looks clustered into 4 groups. This should become more explicit once you performed and visualized the k-means clustering. At this step, I standardized the data as performed in previous exercises and stored the standardized values in Z-income and Z-age columns. Now, we performed k-means clustering using the standardized data. First, I imported the cluster module from the sklearn package and defined the colors and shapes that we used for each cluster. And since I knew that we would be visualizing 6 clusters in all, I defined 6 different colors and shapes. Then, I used a for loop and clustered the data using a different number of clusters, ranging from 2 to 6, and visualized the resulting plots obtained in a subplot. I used a separate for loop to plot each cluster in each subplot, so we can use different shapes for each cluster. Now, by observing the resulting plots, we can see that with too few clusters, we end up with clusters spanning pretty sparse regions in between more densely packed regions. However, with too many, we end up with clusters that border each other but don't seem separated by a region of sparseness. Therefore, 4 clusters seem to capture things very well. I hope this exercise helped you understand how to visualize data and make a decision for the number of clusters that you should choose. The sum of squared errors is the sum of the errors for all data points squared. Error is the difference between a data point and the centroid of its assigned cluster. It can be calculated with the equation you see on the screen. Here, μk is the location of the centroid of cluster K, and each xi is a data point assigned to cluster K. As we increase K, we should expect the sum of squared errors to decrease since there are more centroids. When plotted together, however, there will often be an elbow in the plot where the gain in terms of reduced errors seems to slow for each new cluster. Hence, the plot of sum of squared errors versus number of clusters k will look like you see on the screen right now. A plot of the sum of the squared errors for different values of k showing an elbow at k is equal to 4. Elbow is also called inflection point. Let's go ahead and do another exercise now. Determining the number of clusters using the elbow method. Now in this exercise, we need to determine the number of clusters between 2 and 10 that is best to use for the age and income data using the elbow method with the sum of squared errors. Now in the first step, we imported pandas and load the age and income data from the aging.csv dataset into a data frame named aging_df. Now at this step, we standardize the data as performed in previous exercises and stored the standardized values in zincome and zh columns. Now I copy-pasted a code here and I got a warning message which says that the method .as_matrix will be removed in a future version. So Python suggests us to use .values instead. This is just a warning. It's not going to impact our lesson right now because currently this method .as_matrix is still available. So we need to calculate the sum of squared errors for clusterings using 2 to 10 clusters. But we will start by going through the process for a clustering with k is equal to 2. We imported the cluster module from the sklearn package, cluster the data using k is equal to 2 and save the resulting labels in a variable called cluster_assignments and cluster centers in a variable called centers. This is basically what this code did. Now to perform the calculation for the sum of squared errors, we imported NumPy. We calculated the difference between each data point and the center of its assigned cluster. We squared it and we used the built-in NumPy sum method to sum all of these squared errors together using the code you see on the screen. Now we're going to import matplotlib.pylot for plotting. Now we created a loop through k is equal to 2 to k equal to 10. We calculated the squared error for each and stored the result as a list in a variable called ss. Now finally, we are going to create a plot with k on the x-axis and the squared error on the y-axis. The resulting plot should look like this. Now by observing this plot, you will notice that there is a clear elbow in the plot at k is equal to 4. So we take that as our best number for k. Prior to that, an additional cluster gives us big gains in reducing the sum of squared errors. And beyond that, we seem to be getting diminishing returns.